Dr. Lewe proves water must exist. So here's my explanation of trying to explain Lewe in terms of an explanation of the destruction of a water molecule. So imagine a water molecule. It's being as just a single molecule existing in perfect sphericity, in perfect equilibrium. Imagine there's a force on it, an acceleration, infinite force compressing this molecule, and that this is therefore the inertial frame, and these are two enormous steel plates, imagine them as, and that they're infinitely wide, and that this water molecule therefore can be compressed to extinction. So that if you pressed it and you compress this bubble, this molecule, this is the shape that it will take up. It will become elliptical. This is its existing shape. It's now compressed to that. The jaws are closing. This one's pressing. The zero inertial frame is pressing back, a reaction causing a compression in the water molecule. Continuing on the action, the water molecule is now compressed to that thickness, and it's a huge disc, two-dimensional disc within the two steel plates, but it still exists. It's as thin as it can possibly be, because the next moment it's going to stop existing. But this is the point where logic needs to come in. It's not possible for that water to stop existing. It's impossible. Just think about it. Where does this go? Where does the water go if it's eliminated? It must be somewhere as an entity, or it vanishes. If it vanishes, well then life doesn't exist. Nothing exists because we know water exists. So this can't happen. So this is what I'm imagining now. So we're assuming that the compressive force is actually spherical, so that this piece of plate that we see is actually this shape, and that as you compress it, the water molecule squeezes out, but as it squeezes out, it expands. This space is expanding. That expansive force is also pressing up and down, and so it's pressing against the force here. If there is there's an imbalance of forces here to here, then the pushback of the expansion force of the water can be greater than the force that's pushing there, and so it pushes back, creating a spherical force that's actually pushing on it. So that in some way, the force that's destroying it, or attempting to destroy it, is the force that's actually saving it and keeping it going, keeping it alive. So that the shape of the disc that's created, I'm imagining this is a flat disc, 2 dimensions, is actually like this, with a raised edge. It's just a theoretical position for how we've taken the expansion so far. So we've got it to this point. How big it is, we don't know. How big this gap can be, we don't know. We know that if that closes, it's no longer this shape. There's a hole in the middle of the molecule, and that would make it cease to exist as a molecule. So if the spherical forces has infinite diameter, then the condition is as shown. So if this infinite force has an infinite diameter and yet it's spherical, what happens is that you can analyze it as a single rectangle like this. We're balancing the forces, knowing that this is a sphere. So that the forces that are acting to create this disc, which actually looks like this with the raised edge, looks like this. Here's all the bending forces hitting our straight line, where we're going to end up being. These are the axes of the bending, where we'll see those forces occurring. At the pi split, the 1, 2, 3 split, we've got a split here, where the bending will be forcing through the center, and the angles will be working perfectly in terms of balance of tension, and that there's a center one where there is no tension at all. So here we can see that everywhere that the expanding water is pushing back to create the sphere, apart from at the very center. So the very center is the weakest point. In terms of the water, this is the strongest force. It's going to come down through this line, pushing to the center. The only way that this system can sustain itself is if this expansion continues. The only direction it can expand is wider, fatter, and this gets thinner. And so that's its direction of expansion. The speed of expansion is at c meters per second. So taking that into this, a final drawing here to try to show there's more to come here, but this is our lead into Lewe. So that theoretically, balancing the forces now back to a sphere again, so that I've taken this shape and I've just balanced the forces that I know are acting here, and I've applied them all in here. I haven't drawn them all in because I didn't want to just clutter this. So here's our disc. Here's the balance of our forces, perfectly spherical. Here's our C, our rate of expansion, defining the diameter. How far can it go before the forces balance here and here perfectly? The tension that's created in the surface tension of the sphere is created here, but at twice the diameter. It was that size. It's now this size. So that this tension, surface tension, has a double the radius that it had here. If we just assume that at this diameter, this perfect sphericity, the radius, the diameter of this water molecule is pi, and that the circumference is therefore pi squared, we can bring the same idea down here to say this is now 2 pi. Is this 2 pi squared? What happens here? At this point of tension, where you have the 2 pi and the pi, difference between them, the two, the balance is achieved and it becomes light. That the acceleration of the water, because it's accelerated from here to here, we've only stopped it at the action there, because at C something happens. What happens is it turns into light. And it's the tension between the pi and the 2 pi ratio that defines when that light occurs. Now, when that light occurs, it's going to have a vector and a direction. Look at the potential differences. This is meters per second. We've got plus meters minus seconds in this zone. We've got minus meters minus seconds in this zone. We've got plus meters plus seconds up here. And here we've got minus meters plus seconds. The potential increase, therefore, in the vector is going to be from negative to positive. And from positive to negative. Because you're looking for the difference between the two. You're looking for greatest differences to correct, as entropy requires to do. It will seek for the path of least resistance, the greatest difference, and it will go in that direction. Once it is set up, the light has established itself. It has a vector. It is clockwise because of the potential difference that occurs. What happens is, if it's a clockwise rotation of the system, it must have an inertial frame of reference. That vector of clockwise must be relative to something, and it's relative to the center, and it's relative to this point through the whole of the molecule. That there is a point here against which this rotation is occurring. There is the zero inertial frame of reference, and that is rotating clockwise, anti-clockwise, relative to the clockwise system. So that this center, relative to the system, goes this way, the system goes this way. And the link to Lewe now, for chapter 2. I split this into the 6 portions from Lewe. So you remember, this is his figure 6, where he shows the clockwise moment occurring, and he's taken it to 6 positions. I've just recreated that here. Here are my 6 positions of the wave. Which anyone see that? And here they are, 1, 0, 1, 2, 3, 4, 5, 6. This is an orthogonal wave. And it keeps adjusting to try to fit this pi 2 pi ratio into a pot where it should not fit. Okay, so that you can see that the outside of this molecule, now twice its size, with a tension and bending of light, if it's traveling in this direction, at position 2, we know there is no pushback at all from the center. The light goes, yeah, the light's going to end up at the center. And so that takes us into chapter 2 for Lewe, for the dimension of load. But when you're looking at Lewe, think about it as a definition of load. Load describes what holds a water molecule in one piece. And this is just the beginning of the analysis to visualize it. And then that leads us straight into Lewe. And we're going to look at that line and that load and how you analyze it. Okay, that was chapter 1 of Lewe. Hope that made sense. Look forward to chapter 2. See you soon.